Greetings and welcome to the 9th episode of PHS Physics SOS. Today I'm going to be going over the problems from Chapter 5 on centripetal motion. The first question is question 14, which reads, when a wheel rotates about a fixed axis, do all the points on the wheel have the same tangential speed? And the answer is no. And I'm going to explain this by drawing a wheel. If I have a wheel spinning around its axis, if, say, this, and let's say it's spinning at 60 revolutions per minute, so it's going around once every second. Here's a radius. If this point on the wheel goes around once every second, then it has to travel this entire distance in 1 second. But if this point goes around the wheel in that same period of 1 second, it only has to make this distance. So a point on the wheel that's closer to the center is going to have to travel less distance during the same revolution than a point that's further away. So the answer is no. They'll have the same. While they'll have the same rotational speed, they will not have the same tangential speed. The points further away will have greater tangential speed, just because they're further away. And the next question is question 15. Which says, correct the following statement. The racing car rounds a turn at a constant velocity of 90 miles per hour. Now, if we remember, velocity is a vector. And vectors have direction and magnitude. So, if a car is rounding a turn, let's see, here's our turned road. And if, well, that's terrible, but if we have a car going around this turn, right here, its velocity looks like that. Right here, its velocity looks like that. And right here, its velocity looks like that. So, while so far we've been saying that, oh, this car's velocity is 90 miles per hour, the magnitude of this vector may be 90 miles per hour, but the direction's changing. Right here, the magnitude's, from our perspective, say straight north, then it's like northeast, and now it's east. So he has the same speed of 90 miles per hour, but since velocity has to have a direction associated with it, this is actually a speed of 90 miles per hour. It's a velocity of 90 miles per hour north, or a velocity of 90 miles per hour northeast, or a velocity of 90 miles per hour east. So the correct way to say the statement would be the racing car rounds the turn with a constant speed of 90 miles per hour. The next question is question 16, which says, describe the path of a moving body whose acceleration is constant in magnitude and at all times is perpendicular to the velocity. Okay, so that means here's our object, just a point particle. We have an acceleration that is at all times perpendicular to the velocity. And this is centripetal motion. If you have acceleration that is always perpendicular to the velocity, then that means you're going to be going in a circle. And the reason for that is because acceleration is the change in velocity. So if your acceleration is always perpendicular to your velocity, and here, let me redraw this over here so I have more space. If here's the center of my circle, I have a velocity, if I have a velocity vector like this, and an acceleration vector like this, then since acceleration is my change in velocity, if I just add my acceleration vector to my velocity vector, so if this is A, then my next velocity vector is going to be like this, except it's going to be starting from this velocity vector, so it'll be like that. And then my next acceleration is going to look like that, which would make my next velocity like that, but coming out here. And my next acceleration is going to look like that. And my next velocity is going to look like that, except coming out here. So granted, we've drawn our vectors somewhat squarish-like because I'm not a perfect artist and this turned out a little wonky, but you should be able to get the idea here that if you have an acceleration that's always perpendicular to your velocity, then you're going to end up with circular motion, which is the topic of this chapter. So the answer to question 16 is a circle. It's going to be moving in a circle. The next question is question 20, which says the gas pedal and brakes of a car accelerate and decelerate the car. Could the steering wheel fall into either of those categories? Explain. So this is kind of the same thing as question 15, kind of, or the same concept. Acceleration is a vector, and vectors have direction and magnitude. So while your gas and your brake change the magnitude of your acceleration, it makes you accelerate faster or slower, or it makes you decelerate, the steering wheel changes the direction of your motion, which means you're accelerating one way or accelerating the other way. Because if you're going down the street going straight and then you turn, your velocity has experienced a change. Your velocity was originally going this way and now it's going this way. And as we've said before, a change in velocity is acceleration. So even though you may have the same speed, even though you may be going for like 20 miles an hour into the turn and then still turning at 20 miles an hour, that's a speed. Your acceleration is the change in your velocity. So if you turn your wheel, your velocity was originally, say, 20 miles an hour north, and it ends up being, then 20 miles an hour. I mean, it's kind of like this right here. Your velocity starts, 20 miles an hour north, then 20 miles an hour northeast, then 20 miles an hour east. So while your speed may have stayed the same, your velocity changed because the magnitude changed. And the reason the magnitude of your velocity changed was because the direction of your acceleration changed. Question 22 says, the Emerald Suite, a revolving restaurant at the top of the Space Needle in Seattle, Washington, makes a complete turn once every hour. What is the tangential speed of a customer sitting 12.5 meters from the restaurant center? Okay. So they've given us, it makes one turn every hour. So it goes through 360 degrees per hour, or 2 pi radians per hour. If you don't know what radians are, I'll have a separate segment of the video explaining what they are later. So you just skip to that and then skip back to this, but that'll be at the end. So it's moving 360 degrees per hour, or 2 pi radians per hour. And it says, what is the tangential speed of the customer sitting 12.5 meters from the restaurant center? Okay, so then we know that our radius equals 12.5 meters. So they've given us a angular velocity in omega, and omega is just like a little curly W like that. And they've given us a radius, and they want to know tangential velocity. And tangential velocity, conveniently, is equal to omega times r. And the reason for that is because the units for velocity are usually, in this case, we're going to use meters per second. And the units for omega, our angular velocity, is in, we're going to convert it to, not pi, radians per second. And then our unit for r is meters. So when you multiply these together, you'd be inclined to think that it's meters times radians per second. But radians aren't really a unit. You can't really measure, I mean, it's just, it's really a strange concept, and maybe Miss Casey O'Brien can explain this better, but radians are more of just a measure of angle, but they're not an SI unit, so they're kind of like an imaginary unit, so they just kind of go away. But you can't use degrees, because degrees, by definition, are a degree of something, whereas radians are more of an absolute scale. And to explain that, I'd have to go more into trigonometry, but this is physics, not math. So, that's why this works. It's meters per second equals radians per second times meters, but radians aren't really a unit, so it's meters per second equals meters per second. So, back over here, our velocity equals our omega, but they gave it to us in revolutions per hour. They said 1 revolution per hour, but we want it in radians per second, because normally you give velocities in meters per second, so we're going to give our velocity in meters per second. We're not going to give it in meters per hour. That would be asinine. So first thing we have to do is convert this to radians per second. So multiplied by 1 hour is 3,600 seconds, and you get 0.00175 radians per second, which is going to be your angular velocity. So our tangential velocity is going to be that 0.00175 times our radius, which is 12.5. So that's going to give us our final answer of 0.022 meters per second. That's your tangential velocity at 12.5 meters out from the center of this thing, which goes around once per hour. The next question is question 23, which says, what is the magnitude of the centripetal acceleration of the customer from item 22? And centripetal acceleration is the square of the tangential velocity over the radius. So we're going to take 0.022 squared and divide it by r, which is going to give us 3.81 times 10 to the negative 5th meters per second squared. And again, r is just this. The next question is question 27, which says, why does the water remain in a pail that is whirled in a vertical path as shown in figure 7-16? Figure 7-16 is a guy holding out a pail of water and swinging it in a vertical circle in front of him. And the reason that the water doesn't fly out as it goes around is because the inertia of the water makes it want to fly in the direction of the velocity. It makes it want to go that way. And the velocity is always tangential, but the acceleration is this way. So if the bucket's, on its side and going up, the water's trying to fly out this way, just because that's the direction it's moving in. But then the side of the bucket is keeping the water in. Or when it's at the top, gravity you'd think would make it want to pull down, but the velocity of the water is making it want to push that way because it came up from here. I mean, the answer in the book says water tends to follow a straight line path, and the pail exerts force that maintains circular motion, which basically says objects tend to want to go in a straight line. They don't want to go in a circle. But the thing attaching whatever's going in a circle to the center, in this case the guy's arm attached to the pail, will pull it in a circle and prevent it from flying off at a tangent. And hopefully that wasn't too much of a disjointed explanation, that it actually made sense. The next question is another conceptual question, question 32. And it says, why does mud fly off a rapidly turning wheel? And the answer to this is that if you have a spinning wheel, we're going to imagine this piece of tape, or this roll of tape is a spinning wheel. If you have a spinning wheel and you have something on it, the friction between that little speck of dust or mud or dirt or whatever, the friction between that dirt and the wheel is going to keep it on, unless the inertia of the object exceeds the frictional force between it and the wheel. So in this case, whatever your object is, like the mud. Since the wheel's turning fast enough, the inertia of the mud, its willingness to maintain straight motion or maintain a stationary position. In this case, its willingness to maintain straight motion. Objects want to go in a straight line. They don't want to go in a circle. So its inertia is going to exceed the frictional force, and it's going to fly off at a tangent. The next question is question 40, which says, an airplane is flying in a horizontal circle at a speed of 105 meters per second squared. The 80.0 kilogram pilot does not want his centripetal force to exceed 7.00 times free fall acceleration, otherwise known as 7.00 Gs. And part A says, what is the minimum radius of the circular path? So, what this is saying is, you have this pilot flying in a circle. Why you'd fly in a circle is beyond me, but whatever. And he doesn't want his centripetal acceleration to be greater than 7 times free fall acceleration, or 7 times g. So, centripetal acceleration, we'll call it a sub c, has to be less than or equal to 7 times g. And the way you calculate centripetal acceleration is v squared over the radius of the circle. It has to be, and we're just going to set it equal to 7g to calculate exactly what the maximum it can be, the maximum that the radius can be. So his velocity is 105 meters per second, so we're going to square that, divide by r, and that's equal to 7g, and 7g is equal to 68.6. So we have 105 squared over r equals 68.6. So do a little bit of algebra and you get 105 squared equals 68.6 times r, and 105 squared over 68.6 is going to be equal to r, which will give you r equals 161 meters, which is your answer to part A. Now part B says, at this radius, what is the net force that maintains circular motion exerted on the pilot by the seat belts, the friction between him and the seat, and so forth? What they're asking for is the centripetal force, which we're going to call F sub c. And we know that F equals ma. So what we could do is just take our centripetal acceleration and multiply it by the mass to get the centripetal force, which is what I'm going to do. But there's two ways to do this. You can take the centripetal force the centripetal acceleration you already calculated and multiply by the mass, or you can use an equation for centripetal force, which is mv squared over r, which is really just m times your centripetal acceleration, because this is centripetal acceleration, and if you multiply it by m, you get this. So they're the same thing, it's just different ways of thinking about it. So I'm going to use this one. So our mass is 80 kilograms times our centripetal acceleration, which we never actually calculated. Never mind. So we haven't actually plugged this in yet, so I'm going to be using this equation. So 80 times 105 squared over 161 is going to be equal to 5.48 times 10 to the third newtons, or you can't see that, 5.48 times 10 to the third newtons, also known as 5.48 kilonewtons, because 10 to the third is the prefix for kilo. Either of these answers would be acceptable. The next question is question 43, which says a 2.00 times 10 to the third kilogram car rounds a circular turn of radius 20.0 meters. If the road is flat and if the coefficient of static friction between the tires and the road is 0.70, how fast can the car go without skidding? Okay, so first we're going to draw a free body diagram of the car. So it has the force of gravity down, the normal force upwards. And this is actually a free body diagram as we're looking at the car as it's coming at you. So looking at it from the side, but not like the side of the car, like the front of it. So if we were to draw the car from a top-down view, like we're looking down from the sky, I mean, we'd have the force of gravity downwards, the normal force upwards, but then you have the force pulling it in a circle, turning to the right, which on this diagram is going to be coming out the side. But the question is, what is that force actually coming from? I mean, we could just label it centripetal force, but centripetal force isn't like gravity. It's not just always there. You can't just write centripetal force. It has to be coming from something. Yeah, I mean, it has to be applied by something, which in this case is actually going to be the friction from the tires. So this is going to be our force of friction coming from the tires, because that's what's keeping the car turning. That's the force that's pulling it to the side, pulling it towards the center of the circle, pulling it to the center of the turn that it's going through. Which means that the car can only be going at a maximum speed of v in order for the force of friction to actually be able to keep the car from skidding. So to solve for that maximum velocity, we're going to set the force of friction equal to centripetal force acting on the car, because they're the same thing, they're just calculated in different ways. So the force of friction is static coefficient of friction times our mass times our gravity is equal to mv squared over r. So the m's cancel, and we have mu g times r equals v squared. So if we take the square root, we get root r static g equals v. While this may seem like kind of a weird answer, if you actually work out the units, you're going to get meters per second. So if we have our radius in meters times our coefficient of friction, which by definition, since it's a coefficient, it doesn't actually have any units, times gravity, which is in meters per second squared. So this is going to give us the square root of meters squared over second squared, which will give us meters per second. So this actually works out to give you a speed. And if we plug everything into this, we're going to get the square root of our radius of 20 times our mu of 0.7 times g, which is 9.8. And when you multiply these all out and take the square root of them, you will get a maximum velocity of 12 meters per second. Now what this means is that this car can be going up to 12 meters per second, and the force of friction will be enough to keep the car in uniform circular motion. If it goes any faster than that, it's going to skid out and it won't be experiencing uniform circular motion. So the next problem is question 44, which I believe is similar. It says a 13,500 Newton car traveling at 50.0 kilometers per hour rounds a curve of radius 2.0 times 10 to the second meters. Find the following. A, the centripetal acceleration of the car. Okay, so centripetal acceleration of the car, we know that centripetal acceleration is v squared over r, except they give us our velocity in kilometers per hour, and our radius is in meters. So we're going to change our velocity to meters per second, because that's what we're used to dealing with. So some real quick dimensional analysis. So 50 kilometers per hour times 1,000 meters in 1 kilometer times 3,600 seconds in 1 hour, which gives you 13.9 meters per second. You can't really see that. 13.9 meters per second. So if we just plug that into our equation for centripetal acceleration, we're going to get 13.9 squared over our radius of 2.0 times 10 to the second, which is 200 meters. And when you plug that into your calculator, you will get 0.965 meters per second squared, which is equal to the centripetal acceleration of the car. So part B asks for the force that maintains the centripetal acceleration, and this just means the centripetal force. So to find the centripetal force, the centripetal force is just mass times centripetal acceleration, but they don't give us mass, they give us weight, so we have to take our weight of 13,500 newtons, set it equal to mg, divide by g, and we will get our mass of, let's see, what is our 1,380 kilograms. So when we multiply this by our centripetal acceleration, we'll get our centripetal force. So just to recap real quick, we are given the weight, which we can set equal to mg, divide by g to get our mass, because the weight is just the normal force, which in this case is going to be the force of gravity acting down. And then to get our centripetal force, we have to multiply that mass that we just found times our centripetal acceleration. And when we plug that in, we get 1,330 newtons. Now part C says, find the minimum coefficient of static friction between the tires and the road that will allow the car to round the curve safely. Okay, now, as I mentioned in question 43, the centripetal force, the force that's keeping the car moving in a circular path, is actually applied by the force of friction. The maximum centripetal force that you can have is going to be equal to the maximum force of static friction that can act on the car, which is just going to be the coefficient of static friction they give you times the normal force. So for our case, we want to set force of friction equal to the centripetal force, which is going to be mu times our normal force, which they give us, is going to be equal to our centripetal force, so 1330 newtons. So when we divide these out, we'll get our mu equals 1,330 over 13,500, which is 0.099. Sorry, equals mu static. The next question, which hopefully I have enough room for on this page, is question 48, which reads, an air puck of mass 0.025 kilograms is tied to a string and allowed to revolve in a circular radius of 1.0 meters on a frictionless horizontal surface. The other end of the string passes through a hole in the center of the surface, and the mass of 1.0 kilograms is tied to it, as shown in figure 7-19. The suspended mass remains in equilibrium while the puck revolves on the surface. Okay, so I'm not going to try to draw this because I'm absolutely terrible at drawing things. But just look at the picture in your book and I'll explain to you what's happening. So that puck is undergoing uniform circular motion, except in this case the centripetal force on the puck is supplied by the tension in that string. And the tension in that string is supplied by and is equal to the force of gravity on that weight pulling down on it. So let me go over that real quick again. That puck, which is going in a circle, is experiencing uniform circular motion, and the centripetal force acting on it is supplied by the string, supplied by the tension in the string rather, and the tension in the string is supplied by the weight at the other end of it. And the tension of the string is also equal to the force of gravity on the weight at the other end of it. And obviously the way to calculate the force of gravity on a weight is just going to be its mass times the acceleration due to gravity. And they give us that the mass, so f of x, or we're just going to call it f of x, the force that they're looking for in part A, is going to be equal to the mass of the weight times gravity, which is equal to 1.0 kilograms times 9.8 meters per second squared, which gives us 9.8 newtons. Now part B says, what is the linear speed of the puck, otherwise known as the tangential velocity? So the way to solve for the linear speed is to set the centripetal force equal to this. Equal to this force pulling down on it, because as we said in part A, the centripetal force that's acting on the puck is supplied by the tension in the string, which is supplied by the by the force of gravity acting on the weight pulling down. So if we set that force of gravity acting on the weight pulling down equal to the centripetal force acting on the puck, we can solve for the tangential velocity of the puck, because we know that centripetal force is equal to mv squared over r. And we know our mass, and we know our radius. Yes, we do. So we just plug them in and solve. So 9.8 is going to be equal to our mass, which is 0.025 times velocity squared over our radius, which is just 1. So 9.8 divided by 0.025 equals v squared. Take the square root, and you get velocity. So when you plug that into your calculator, you're going to get a velocity of 2.0 times 10 to the first meters per second, otherwise known as 20 meters per second. The final question, which I've unfortunately had to go onto a new page for, is question 49, which admittedly is a bit tough, but should make sense. Sorry for the squeaky chair, this mic picks up too much. And question 49 reads, in a popular amusement park ride, a cylinder of radius 3.00 meters is set in rotation at an angular speed of 5.00 radians per second, as shown in figure 7-20. The floor then drops away, leaving the rider suspended against the wall in a vertical position. What minimum coefficient of friction between a rider's clothing and the wall of the cylinder is needed to keep the rider from slipping? And it says, recall that the force of static friction is equal to mu times the normal force, while the normal force is the force that maintains the circular motion. And what the heck does that mean? So, if we go ahead and draw our free body diagram for our rider, and we're looking at him from the side, like as if you're right next to him on this ride, like he's standing here and you're standing here, and you look over at him, and you're looking at him from his side. So, you're going to see the force of gravity pulling down on him. Well, you're not going to see it, that'd be cool, but the centripetal force pulling this way, but there's no floor under it. So what's pulling him upwards? Well, the answer is, what's pulling him upwards is actually the force of friction, due to the centripetal force, which in this case is kind of acting like a normal force, because normal force is perpendicular to the surface that's keeping you up, so to speak. And in this case, since he doesn't have his feet on the ground, the only thing that's keeping him up, so to speak, is the fact that his back is pushed flat against the wall, and it's the cold weld bonds between his sweater or sweatshirt or jacket or shirt or whatever, and the metal that are sticking and not letting him fall down. So the way to solve for the coefficient of friction, the minimum coefficient of friction between the rider and the wall, is to set this force of friction equal to mu times the normal force. But what's the normal force? In this case, the normal force is actually this. So the force of friction, and the minimum force of friction to keep him up is going to be the force of gravity downwards, because if the friction acting on you pulling you up isn't greater than the gravity pulling you down, you're kind of SOL. So yeah, the force of friction pulling upwards has to be equal to mu times the normal force. Now, the force of friction we know in this case is going to have to be equal to, at a minimum, the force of gravity, which is going to be mu times, and we know that the normal force is equal to the centripetal force, which is mv squared over r. So mg equals mu times mv squared over r. Mu's cancel, and we get g equals mu times v squared over r. Now if we multiply and do little multiplication and division, we multiply by r, we get gr, and then divide by v squared over v squared equals mu sub s. And they give you all this, or you either know or they give you all this information. Actually, no, hang on. We do have to calculate the tangential velocity. So, g we know is 9.8. The radius they gave us is 3.0. But the tangential velocity, we don't know yet. However, they give us the tools to find it, because as you should know from reading this chapter, the tangential velocity is going to be equal to the radius times the angular velocity. And they give you the angular velocity in the unit we need, radians per second. So our tangential velocity is going to be equal to the radius of 3 meters times the angular velocity of 5 radians per second. So this is going to be equal to 15. Now, when you plug this all in here, you get g times r over 15 squared, which is 225, equals your coefficient of static friction, which is equal to 0.131. Now, I'd like to do a quick run through on what radians are for anyone that may have not learned it in math yet. Radians are another unit of measuring an angle. Normally, when you have a circle, and yeah, I can't draw great circles, if you go all the way around the circle, again, I can't draw great circles, God. If you go all the way around the circle, it's going to be equal to 360 degrees. Now, another way to express that is in radians. Now, the number of radians around a circle is going to be 2 pi. So there are 2 pi radians in one revolution of a circle. Now, what that means is that every time you go around the circle, you've gone through, let's see, what's 2 pi? 2 times 3.14 is about 6.28. So you've gone, one revolution is approximately equal to 6.28 radians, or 2 pi radians. And generally you want to use pi, but when you plug it into your calculator, you actually do have to, I mean, you could just press the pi button or plug in this. Either way. And the way to convert from degrees to radians is you take your degrees, so you have, let's say, 360 degrees, and you multiply that by pi over 180. So to get from degrees to radians, you multiply by pi over 180. Conversely, to get from radians to degrees, you need to multiply by 180 over pi, just the inverse of this. So let's do a few, can't speak today, a few real quick examples, and then we'll get onto the physics. Or you can get onto the physics, I guess. This is probably going to end up being at the end of the video. So if we have 90 degrees, and we want to figure out what that is in radians, we multiply by pi over 180, and 90 over 180 is 1/2, so we get 1/2 times pi, which is equal to pi over 2. So that means that in 90 degrees, or in a quarter of this circle, that is pi over 2 radians. So that means if right here is 0 degrees, then up to here is pi over 2 radians. Then, as you can probably guess, 180 degrees is another pi over 2 radians, and if you add pi over 2 plus pi over 2, it's the same, it's just equal to pi, because it's half of a pi plus half of a pi equals a whole pi. Let's do one more quick example. Let's say we want to go from, you're probably not going to have to do this because unless they want the answer in degrees or something, because for the sake of circular motion in physics, you're going to have to calculate absolutely everything in radians. You cannot use degrees. I could explain it, but I'd have to go into graphing. Sine functions and stuff like that, and it's just really gross. It's just accept the fact that you need to use radians and just learn radians. So let's say you want to go from 3 pi over 4 radians to degrees, which is multiplied by 180 over pi, and we will get, see the pi's cancel, and you get 135 degrees, which is about right here. So if you start here and go to here, this whole angle here is 3 pi over 4 radians, or 135 degrees. Thank you for watching this episode of PHS Physics SOS. I hope you have found it helpful. If you have any more questions on any of these problems, or any other problems, or just concepts in general, feel free to leave a comment in the YouTube section below, or leave a comment on the Facebook group, or message me personally on Facebook, or whatever. Get a hold of me on Skype, text me, whatever, and I'll help you as best I can. Thank you for watching.